Hello, my name is Jessica Martinez and I am a student in multivariable calculus. Today I'm going to talk about how multivariable calculus is relevant, related, and incorporated in roller coasters. To begin with, the track of a roller coaster is usually a curve in 3D space, meaning there is normally an x-axis, a y-axis, and a z-axis. Because it could be described in terms of x, y, and z, and because it is also in a three-dimensional space, the track of a roller coaster can be described by the functions x of t, y of t, and z of t, and they help define the position of a roller coaster at any specific time, which is usually in seconds. Furthermore, these functions help describe the horizontal and vertical position and components of the roller coaster as it moves along the track of the road. Um, the shape of the track also helps determine how the roller coaster moves up, how it goes down, and also how the roller coaster moves through the loops and the manners in which the roller coaster turns. And furthermore, we have the arc length. Like I previously mentioned, the arc length is the term used to describe the distance traveled. So in this case, the arc length will be the distance that the roller coaster travels at a specific time. To find the total distance that the roller coaster travels along a specific path on the track, we need to find the arc length of the path. Normally, there's a mathematical way to find this, which is the formula. And the formula also takes into account the x of t, y of t, and z of t functions. So let's take a look here. So right here we have the arc length formula. So the formula is as follows. Arc length equals the integral from a to b, which will normally be a specific time in seconds, depending on the time it takes for the roller coaster to run around the track. And that integral would be you would integrate that for the radical of prime x of t squared plus prime y of t squared plus z of t squared, and then you would find the integral with respect to t. Furthermore, the arc length can also be illustrated as the integral from a to b for the magnitude of r prime t with respect to t. And so basically the second formula is also the arc length, but it tells you the integral of speed, and it also tells you like the magnitude of velocity. So in this case, the speed basically refers to the speed of the roller coaster. However, velocity is speed and direction of the roller coaster. But since we're taking the magnitude of the velocity, it would be like in the scalar component, which gives you the speed. So overall, these go hand to hand. Now let's take a specific look, for example. So here we have a problem. We have to find the arc length of a roller coaster if the curve is r of t equals t in the I component plus 4 over 3 t to the power of 3 over 2 in the j component plus 1/2 times t squared in the k component. And we're trying to find the arc length of the roller coaster given this information, but it's also important to understand that we're finding the arc length from 0 seconds to 3 seconds. So even though the roller coaster probably lasted over 3 seconds, we're only focusing on how much the roller coaster traveled between those 3 seconds. So the distance that the roller coaster traveled in 3 seconds. So the first step we have to do in order to find the arc length would be to remember the formula. So as previously mentioned in the first slide, the arc length can also be found using the integral from a to b of the magnitude of r prime of t with respect to t. So in other words, because we are given the curve, which is r of t equals t plus 4 over 3 times t to the power of 3 over 2 plus 1/2 times t squared. So because we're given the curve, we can find the derivative of the curve, and then we can also find the magnitude. So let's take a look at the first step. So the first step would be to find the derivative of t with respect to the I component, the j component, and the k component. So let's take a look at the I component first. So the I component of the curve is t. When we integrate with respect to t, we find the derivative. So when you find the derivative of t, we drop the power and we multiply it. So for example, the derivative of t would be 1 for the I component. Then we move on to finding the component for j. So for j, we are given 4 over 3 times t to the power of 3 over 2. Once we have this, we find the derivative with respect to t. So basically, t to the power of 3 over 2 is derived, and it becomes t to the power of 1/2. However, it's important to remember that you have to multiply it by 4 over 3. When you multiply it, you're able to simplify it to get 2. Therefore, your I component, when you find the derivative, becomes 2 times t to the power of 1/2 in the j component. Last but not least, when we take a look at the k component, you have 1/2 times t squared. When you take the derivative of the k component, you drop the exponent, you subtract 1, and then you multiply it. Therefore, 1/2 times t squared becomes t and the k component. Now we have just found the derivative of the curve, aka r prime of t, which is 1 times I plus 2 times t to the power of 1/2 in the j component plus t to the power of 1 in the k component. So because we know this information, we can move on to find the magnitude. So basically, when you find the magnitude, you square the I component, the j component, and the k component, and after you square it, you will multiply it. So in this case, when I find the magnitude, I get the radical of 1 plus 4t plus t squared. Upon further simplification and after adding and subtracting, we can basically simplify the magnitude to get the radical of t plus 2 squared minus 3. So we now just completed the first step of finding the magnitude, and because we know the magnitude now, we can integrate it with respect to t and from the time interval of 0 seconds to 3 seconds. Okay, so now, like I previously mentioned, we now have the magnitude, so we're now going to integrate the magnitude. So when we take a look here, we're basically integrating radical of t plus 2 squared minus 3. And the first thing we can do in order to make the magnitude easier to integrate is that we can use trig substitution. So in this case, we have to remember that tan squared theta equals secant theta minus 1 because it is an identity that we can use further down the line. The first thing we're going to do is we're going to do t plus 2 equals rad 3 times secant theta. Since we're basically using substitution, we're going to find the derivative with respect to t. Therefore, d of t, the derivative of t, equals rad 3 times secant theta times tangent theta with respect to theta. Because we know this information now, we can substitute our values to the original equation. Therefore, this will give us rad 3 secant squared minus 3 times rad 3 times secant theta times tangent theta with respect to theta. However, it's important to remember that we also have to keep in mind the values of the integrals. So we're going to write on the left hand side as a reminder that t equals 2 and t equals 0, because down the line we want to convert those to theta values or convert the function to a function of t. Furthermore, we're going to continue and simplify, and we're going to get 3 times secant theta times tan squared theta with respect to theta. And then once we have our integral simplified, we can further apply partial derivatives. So in this case, we're going to find the derivative of 3 minus secant theta. And for our integral, we're going to use secant squared theta. And because we have to find the integral and we have to find the derivative, it would be easier if we do a chart. So take a look here. When you look at the chart, the top row tells you what to do, when then the second row will tell you what you're doing. So the first row is going to be positive, and you're going to find the derivative of 3 minus secant theta, and you're going to integrate secant squared theta. The second row, or the last row, it will be negative, and you're going to find the derivative of 3 times secant theta times tangent theta, and you're going to find the integral of tangent theta. And then once you put this all together, you're going to find the integral of negative 3 secant theta times tan squared theta with respect to theta. And then you're going to continue using trig substitution, and then you're going to simplify. And then what really helps to find the distance out of the roller coaster is to use trig substitution and to draw out the triangle, because in doing so you're going to be able to convert back from theta values to values of t. And so upon further simplification, we're going to get 2 times rad 13 minus 3 over 2 times natural log of the absolute value of 4 over rad 3 plus rad 13 over rad 3 minus 1 plus 3 over 2 times the natural log of the absolute value of 2 over rad 3 plus 1 over rad 3. And then this value already takes into account the time between 0 and 2 seconds, as you can see in the previous work. And from here on, it's recommended to use a calculator just because the values are very difficult to compute mentally or on the side. And then once we compute the calculations, we are given the distance that the roller coaster travels. So in this case, the roller coaster will travel a specific distance between 0 seconds to 3 seconds. Thank you.